Good morning, respected teachers and dear friends. I'm Arunam Datar, and today we are excited to take you on a fascinating journey.
And I'm Rishi Mehta. We'll dive into a topic that powers our modern world, the physics behind engines.
But first, what exactly is an engine?
By definition, an engine is a device that produces power which helps the vehicle move.
Now, let's rewind and look at the fascinating history of how engines came to be.
Ancient machines utilized human, animal, water, wind, and steam power. Capstans and treadmills were common in ancient Greece and Rome. By the 1st century AD, cattle powered mills and water wheels spread across the Roman Empire. The hero of Alexandria invented winds and steam powered devices, often for religious purposes.
The Industrial Revolution transformed engines with James Watt's steam engine in the late 1700s, enabling factories and railways. Internal combustion engines emerged in France, refined by inventors like Barsanti and Lenoir. In 1876, the Otto cycle introduced a compact, powerful engine design, revolutionizing transportation.
Carl Benz's Volkswagen Beetle popularized four-stroke Otto-cycle gasoline engines. Diesel engines known for efficiency became common in heavy vehicles. Benz's 1896 Boxer engine saw use in cars and aircraft, marking the era when engines powered everything from ships to planes.
Ford's Model T featured a 2.9-liter four-cylinder engine, making cars affordable and accessible. Ford's assembly line transformed manufacturing, setting a standard that revolutionized the automotive industry.
The 2010s saw Tesla and others lead into electric and hybrid engines, combining efficient batteries, high torque, and regenerative braking. These innovations focus on sustainability, reducing reliance on fossil fuels, and driving eco-friendly transport.
The first law of thermodynamics focuses on the conservation of energy, explaining how an engine converts chemical energy into mechanical energy. The second law of thermodynamics explains why some energy from combustion is lost as heat rather than being utilized completely. Newton's laws also explain the workings of an engine. The first law explains the continuous motion of the piston and the crankshaft. The second law explains how combustion generates force to move the pistons, while the third law shows that combustion pushes the piston down, while the crankshaft provides a counterweight, thus pushing it back up. Boyle's law explains that as cylinder volume decreases during compression, the pressure and the temperature increase, and after ignition, this high pressure expansion drives the piston, converting fuel energy into mechanical energy. Now let's understand the first two laws of thermodynamics in more depth. The first law of thermodynamics is central to engines and is expressed as delta Q is equal to delta U plus W. Delta Q is the heat energy added, which represents the fuel combustion. Delta U represents the internal energy changes, that are the changes in pressure and the temperature of the gases. And W is the work output, which in engines is mechanical energy to power. This equation explains how fuel's chemical energy converts into mechanical energy, driving engine operation. It balances heat output, internal energy changes, and the work output, forming the foundation of the internal combustion engine design and thermodynamic cycles like the Otto cycle for efficiency and performance. The second law of thermodynamics is fundamental to understanding engine efficiency and is expressed as delta S is greater than or equal to Q divided by T. Here, delta S represents the change in entropy, which is a measurement of energy dispersion. Q is the heat energy transfer and T is the absolute temperature at which this heat transfer occurs. This law highlights that energy transformations are never 100% efficient and some energy is always lost as heat, increasing entropy in the system. This principle explains why chemical energy is never fully converted into mechanical energy. Innovations like turbochargers try to minimize this heat loss.
Before understanding how an engine works, we need to clear our fundamentals about energy sources of an engine. Fossil fuel based engines utilize chemical energies from combustion, where fuel releases heat energy, which the engine converts into mechanical work. Petrol engines use spark plugs for ignition, producing quick high energy bursts with a high power to weight ratio, ideal for lighter vehicles. However, they are less fuel efficient than diesel engines. Diesel engines rely on high compression for ignition, achieving 20 to 25% more fuel efficiency than petrol. Diesel's denser energy content provides higher mileage, making it popular for trucks and heavy duty vehicles, though they are often prone to overheating. Compressed natural gas emits lower carbon emissions and pollutants, making them more eco friendly than petrol and diesel. While CNG has lower energy density, its environmental benefits make it popular in urban transits and private vehicles. However, they have a limited range and long refueling time.
Today we will be exploring the two types of combustion engines, internal and external. Internal combustion engines generate power by igniting fuel in a confined space, creating expanding hot gases that drive pistons or turbine blades. This process, fueled by air, converts chemical energy into mechanical work to power vehicles. External combustion engines generate power by burning fuel outside the engine to produce steam or heated gases. This energy drives pistons or turbines, converting thermal energy into mechanical work for applications like locomotives and power plants. Spark ignition engines, a type of internal combustion engine, use a spark plug to ignite a compressed air fuel mixture. The resulting explosion creates a rotational force that drives the engine's components, with exhaust gases adding thrust in jet engines or enhancing piston movement in reciprocating engines. Compression ignition engines ignite fuel through the high pressure air compression rather than a spark plug. Compressed air is heated and fuel injected into this air spontaneously ignites. The combustion drives the piston and generates additional thrust in diesel engines, which are more fuel efficient and commonly used in diesel vehicles and heavy machinery.
Another important aspect of an engine is its layout. In simple terms, it refers to the arrangement of cylinders in an engine. In an inline engine, the cylinders are arranged in a straight line, vertically or horizontally, for space efficiency. Commonly found in compact cars and motorcycles, the design is simple, cost effective, and fuel efficient with reduced friction. Its straight layout makes parts more accessible for easier servicing. A V-shaped engine arranges cylinder in two angled rows, usually at 60 degrees or at 90 degrees, forming a V shape, allowing for more cylinders in less space. This engine type is preferred in sports cars, trucks, and luxury vehicles for its compact design and higher power output. In flat or boxer engine, the cylinders lie flat and face opposite each other, distributing mass evenly and creating a low center of gravity. Used in select sports cars, this engine enhances stability and handling while reducing vibrations due to opposing cylinder design. Unlike traditional piston engines, the rotary or the Wankel engine uses a rotating triangular rotor within an oval housing for power. Known for its smooth power delivery and a fewer moving parts, this compact engine is ideal for sports car.
The four-stroke cycle, which you may remember as the Otto cycle, is essentially how an engine generates power. It explains the steps in a piston's operation. The first stage is intake. As the intake valve opens, the piston moves down, drawing an air-fuel mixture into the cylinder. This creates a charge for combustion and fills the cylinder to prepare for the next stage. The second stage is compression. The intake valve closes and the piston moves upward, compressing the air-fuel mixture tightly. This compression increases the mixture's potential energy, making it more explosive. The third stage is power. A spark ignites the whole compressed air-fuel mixture, causing a combustion. that forces the piston downward with power. This downstroke drives the crankshaft, converting chemical energy into mechanical work. The fourth and final stage is exhaust. The exhaust valve opens as the piston moves back up, pushing out the burnt gases from the cylinder. This expels the waste and prepares the cylinder for a fresh intake of the air-fuel mix, starting the next cycle.
Coming to the components of an engine. It begins with a reciprocating system which generates engine power. Pistons move up and down in the cylinders, drive by combustion, converting fuel energy into motion. Connecting rods link pistons to the crankshaft. The rotating assembly drives engine movement. The crankshaft converts the pistons' up and down motion into rotational force, which powers the wheels. The flywheel adds momentum, making power delivery smooth. The valve train manages air and fuel flow. The camshaft opens and closes the intake and exhaust valves in sync with the pistons for efficient combustion. Valves regulate airflow by allowing fresh fuel-air mix and letting out exhaust gases. The fuel injection system delivers fuel to the combustion chambers. Fuel injectors spray fuel into the cylinders for controlled combustion, with the fuel pump supplying pressurized fuel into the injectors for fast delivery.
Let's discuss the limitations of a combustion engine. First is inefficiency and heat loss. Combustion engines waste significant energy as heat, achieving limited thermal efficiency. You may be surprised, but petrol engines only have an efficiency of 25 to 30% and diesel engines up to 40%. Emissions and scarcity of resources are also great limitations. They emit harmful pollutants that destroy ecosystems and which rely on finite fossil fuels, impacting sustainability. Often, high-performance engines are heavy and take up considerable space, giving them a limited power-to-weight ratio and making them unable to be used in compact or lightweight designs. As the world races behind more powerful and faster engines, the dependence on cooling and lubrication systems increases. Combustion engines require intricate systems to manage heat and friction, making larger engines significantly more complex and demanding higher maintenance. However, there are systems to mitigate the effects of these limitations. One of them is the forced induction system. They are systems used to improve engine performance by compressing the air entering the combustion chamber. These systems increase air pressure, enabling the engine to burn more fuel and generate greater power without growing in size, boosting efficiency and performance.
Exhaust gases spin a turbine in the turbine section, which drives a connected compressor wheel in the compression section. The compressor pulls in fresh air, compresses it, and sends it into the engine. This increases air density, improving combustion and engine power.
A screw supercharger operates using two meshing helical rotors to compress incoming air. As the rotors spin, they trap and compress air in the spaces between them, reducing its volume and increasing its pressure. This compressed air is then delivered directly to the engine, improving air density and enabling better combustion for greater engine power and efficiency.
This journey explored technology, physics, and the philosophies driving progress. We explored how curiosity, innovation, and responsibility drive advancements, balancing progress with sustainability. We sincerely thank Leo Sir for this opportunity and hope our project has inspired you to embrace curiosity and the pursuit of knowledge.
It reminded us to find the extraordinary in the ordinary and appreciate the brilliance of everyday technologies. The whole process taught us a lot, from the insides of engines to PowerPoint and video editing.